Alright, today's lecture is on force and pressure and how they're related. You've come to know pressure from thermo or physics or chemistry or several other topics that you may have come across, or even from the Weather Channel. However, now we're going to look at pressure in a slightly different sense, how it relates to force. Usually they don't talk about that per se in the Weather Channel, except when you're dealing with tornadoes. And chemistry, they're generally interested in PV equal to MRT, so they're looking for state changes here. Physics, they may start with that, dealing with the forces and dealing with pressure, and thermo is interested in state changes. In this course, we're interested in, for say, how the pressure may influence an object by forcing it in a particular direction. So let's start by looking at essentially a doorstop. If you look at a doorstop, there's a certain distance into the page. There's a pressure all around this. However, there's a force as a result of the pressure that occurs in this manner. So this force is equal to the pressure times that area. Now, if we stop at this particular point, there is something in this topic that you need to be aware of. We'll call this force 1, we'll call this force 2, and we'll call this force 3. Each force has a particular vector component. So this means that there has to be a vector component on this side of the equation. But pressure is just simply a number or a scalar. There is no vector component associated with it. You know, when someone says 14.7 pounds per square inch, it's just a scalar. So the area must have a vector component associated with it. And for right now, we're going to put the vector component over the top of the area, but we'll talk about how that is actually distributed in a second. Pressure times area 1. Now let's start talking about the area. In other words, force only comes from a pressure and directed by the area. So the only way you can get a force out of something is have a pressure and an area associated with it. So let's take a look at this. Let's assume that for say the units here, let's just pick a number and say, for example, we're going to say area 2 is equal to this distance, which we'll just arbitrarily pick it to be 1. But what is the vector component associated with this? Let's redraw our vector, our doorstop. Now what generally happens in mathematics, and we're going to stick to this, is the area is essentially a vector pointing perpendicular from the surface. Now this happens to be a flat surface here, a flat surface here, and a flat surface here. So if we look at this area is simply equal to, which would be area 2, 1 I. Now that's given that we've chosen the coordinates to look like this. This area 3 happens to be what? Now here's where we have to sort of take a quick look at it and decide what we're going to do here. Let's say, for example, this just happens to be 45 degrees. I'm going to make my life easy. It doesn't look 45 degrees. If it were 45 degrees, maybe I should make it 30 degrees. Well, let's just stick with 45 right now. So if it were 45, it would look more like that. So let's assume it's 45 and that this drawing up here is skewed a little bit. If that's the case, then this area is the same as that area. And it happens to be going in the negative y direction, so I really should have put a minus 1j. I could just call this I, call this minus j. Now here's the key. What is this vector? And I called it area 1. Well, if this distance were 1, say into the page here, it's a distance 1, so that means 1, this distance being 1, and the distance in the page 1 would be 1 times 1 would give you 1. So that means this distance obviously looks like it's larger than that distance, and it turns out to be square root of 1 squared plus another 1 squared, square root of 2. Now I forgot my dimensions here. Now that's the length, or I mean the magnitude of that area. But that is not the vector component. Now, here's where it becomes very interesting. This is obviously, so I really should have put this over it. So now I've got a vector which comes up, goes like that. Now, you know that this times this, so if I say this is a vector of length L, and this is 45 degrees as well, then this has to be a vector of length L. So that would mean that L squared plus L squared square root has to be the length of that vector. But that vector was square root of 2, so that gives you the fact that L was equal to 1 on both of these. So this vector's length is the same as the area over here. I'm sorry, it really should be the area over here. This vector's length is the same as the length of the vector over here. So that means this is equal to, this vector is in the minus, so I would have minus I. This vector is plus j. Now think about that for a minute, because that gives you a vector component for these areas. Now again, this vector ends up being, the vector right there ends up being the same length as that vector, and this vector ends up being the same length as that vector. So now let's start representing these. Let's start looking at the one that's the hardest first. F1, it would be the pressure, and I'll carry it as a P, times minus I plus J. F2. F2 is this one. It's just equal to the pressure. What's area 2? Let me find it. Area 2 is this one. I. And force 3, pressure times this vector, area 3, which is just minus j. Now in statics, we do something that's just sum of the forces equal to 0. But we don't know that that's necessarily 0. Let's just take a look at it. So let's sum the vectors here. So we're just going to add F1, F2, and F3 here is essentially adding the right-hand sides. So sum of the forces here would be F1, F2, F3. Let's just grab it. P minus I plus J plus P times I plus P times a minus J. And as it turns out, the best thing to do is look at the component-wise basis of it. what you get is minus p from this term plus p from that term. You get plus p from this term times that, and then you got minus p from that. So essentially you get 0. Hence the title of all this section, Fluid Statics. Sum of the forces on all this stuff is going to be 0. By that same matter, sum of the moments is going to be all 0. So things are going to look a lot like statics, except there's going to be the word fluids buried in there. So with that in mind, that's a decent introduction here. And what I hope you came away with was the fact that although pressure is represented in a lot of topics, it's a scalar. It's nothing but a scalar. Even though my drawing was skewed here, I hope you got out of it that the pressure doesn't dictate the force. The pressure and the area dictate the force. The direction of the force has all to do with the area, direction of the area. So the direction here has to do with this. So you look at these in vector components, and it starts making a little bit better sense. So with that, we're done.